Hello everyone, welcome to topic 2, atomic structure. This topic is composed of two subtopics, the nuclear atom and electron configuration. Let's begin with the first topic, the nuclear atom. As I mentioned in my previous videos, the vocabularies highlighted in yellow are frequently tested by IB. IB might ask for the definitions of these terms. Keep this in mind. The atom is the smallest part of an element that can be broken down into subatomic particles such as protons, neutrons, and electrons. All atoms are known to be made up of these three fundamental subatomic particles. However, there is an exception. The hydrogen atom is only composed of one proton and one electron and holds no neutrons. The picture above gives us a brief illustration of an atom. As you can see, there is a nucleus in the center of an atom and electrons surrounding the atom. Though this illustration has its limitations, it still gives us a good understanding of the components of an atom. There are some important information you should know about the atom. Atoms contain a positively charged dense nucleus composed of protons and neutrons, which are known as nucleons. Electrons are negatively charged atoms that occupy the space outside the nucleus. They are usually found in energy levels or energy shells. Also, much of the atom is empty space. The chart above compares the mass and charge of the subatomic particles. Let's first look at the mass. By comparing the mass of the subatomic particles, you can see that the mass of an electron is negligible when comparing it to the mass of a proton and neutron. How about charge? The neutrons are neutral particles. An electron is assigned a relative value of -1, and a proton, which carries the same charge but different sign as an electron, will have a relative charge value of +1. All atoms are neutral, so it contains an equal number of protons and electrons. However, atoms can gain or lose electrons and form ions. This will make them have charge. Now, let's take a look at the shorthand notations for an atom and ion. First, X refers to the type of element in interest. A, the mass number, refers to the total number of protons and neutrons. Z, the atomic number, refers to the number of protons in the nucleus. In an atom, Z will also refer to the number of electrons. N, the charge, will be set as 0 for neutral atoms. However, when one or more electrons are lost, the atom will become a positive ion, and when one or more electrons are gained, the atom will become a negative ion. Isotopes are atoms with the same number of protons but different number of neutrons. All atoms of the same element must have the same number of protons. However, they may have a different number of neutrons. Let's look at the example chlorine-35 and chlorine-37. Since the atoms are both chlorine, they will have the same number of protons, 17. However, you can see that they have different mass numbers. Chlorine-35 has a mass number of 35, and chlorine-37 has a mass number of 37. Since mass number is the total number of protons and neutrons, we can easily calculate the number of neutrons for the isotopes. The number of neutrons for chlorine-35 will be 18, and the number of neutrons for chlorine-37 will be 20. Because isotopes have the same number of protons, they will also have the same number of electrons. As chemical properties are related to the number of electrons, we can say that the isotopes of the same element will have identical chemical properties. However, because they have different mass, their physical properties will be different. Next, relative atomic mass. Relative atomic mass is the weighted mean of all the naturally occurring isotopes of the element relative to carbon-12. Let's go back to the example. The naturally occurring chlorine, or the natural abundance of chlorine, contains 75% of chlorine-35 and 25% of chlorine-37. The weighted mean of all the naturally occurring isotopes of chlorine will be calculated by taking into account the natural abundances of each chlorine-35 and chlorine-37. So if you add 0.75 times 35 to 0.25 times 37, we will get an answer of 35.5 grams per mole, which will be the relative atomic mass of chlorine. Let's look at this IB question. This question is about relative atomic mass, and the underlying concept is similar to the example question in the previous slide. Let's look at the question. Number 1. Define the term relative atomic mass. This is pretty simple, right? The definition of relative atomic mass is the weighted mean of all the naturally occurring isotopes of the element relative to carbon-12. Second question. Calculate the relative atomic mass of the sample of germanium, giving your answer to 2 decimal places. This question is very similar to the previous example question. So in order to find the relative atomic mass of germanium, we need to take into account all the relative abundances of each isotope. We can do this by multiplying the mass number of each isotope to its relative abundance and adding them up all together. Then we will get an answer of 72.89 grams per mole. Relative atomic mass can be determined by a mass spectrometer. This is a mass spectrometer. The mass spectrometer is used to determine the relative atomic mass of an element from its isotopic composition. Let's look at stage 1. A vaporized sample is injected into the instrument, and it is ionized by an electron beam. The ions are then accelerated in the electric field and deflected by an external magnetic field. The amount of deflection depends on the mass and charge of the ion. The smaller the mass and higher the charge, the greater the deflection. At last, a detector will record the mass-charge ratio of the ions. Electromagnetic spectrum. Electromagnetic radiation is a form of energy that is characterized by wavelength, frequency, and color. These waves possess a wide range of wavelengths, ranging from low to high energy waves. The electromagnetic spectrum is a spectrum of wavelengths that comprise different types of electromagnetic radiations. Looking at the spectrum above, we can see that the waves range from radio waves with low energy, low frequency, and long wavelengths, to gamma radiations with high energy, high frequency, and short wavelengths. You can also see the visible region in the circled area. Atomic emission spectra. White light is made up of all the colors of the spectrum. We say that the sun emits white light. When the light is passed through a prism, a continuous spectrum of all the colors, or wavelengths, is obtained. You can see the continuous spectrum right here. The continuous spectrum contains light of all wavelengths. When energy is applied to individual elements, they emit a spectrum, with emissions at particular wavelengths. Each element has its own spectrum, and this is known as a line spectrum. As shown above, you can see that the line spectrum consists of discrete lines that are not continuous. These lines converge at high energy. Line spectrum contains emissions at particular wavelengths, and it is particular to individual elements. Atomic emission spectra. In an atom, electrons exist in fixed energy levels, which are identified by the discrete lines. When energy is applied, electrons gain energy and are excited from the lowest ground state to an excited state. This is illustrated in bullet 1, where an electron is excited from the ground state to a higher energy level. Ground state refers to the lowest energy level and is indicated as n equals 1. On the other hand, electrons emit energy when they are dropped from a higher level to a lower level. The energy corresponds to a particular wavelength. This is illustrated in bullet 2, where an electron is dropped from a higher energy level to a lower energy level. Specifically, Electrons returning to the ground state, where n equals 1, the series of lines occur in the UV region, as it involves the greatest energy change. Electrons returning to the second energy level, n equals 2, involve series of lines occurring in the visible region, and electrons returning to the third energy level, n equals 3, involve lines occurring in the infrared region. As mentioned before, lines converge at high energy.